Welcome to This Explainer. Today, we're diving into one of the most mind-bending concepts in all of physics, how gravity literally warps the fabric of time. We're going to take a journey from the terrifying edge of supermassive black holes out in the deep cosmos, straight back down to Earth, to look at the very real technology sitting in your pocket right now. For every hour I spend here, years pass on Earth. If you've seen the movie Interstellar, you know exactly what I'm talking about. That line probably gave you chills, right? It's a moment of pure existential dread. But here's the really fascinating thing. That isn't just Hollywood magic cooked up to make us cry. That famous line perfectly captures the terrifying, mesmerizing reality of the universe that we are exploring today.
And it forces us to ask a really fundamental question. Does gravity actually break time? Like, is this just some brilliant sci-fi plot device? Or is it an actual, measurable physical reality that affects us every single day? It's kind of hard to wrap our heads around the idea that time isn't just a constant ticking clock for everyone everywhere. But spoiler alert, this distortion of time is incredibly real. Okay, so here is our roadmap for today. We're going to cover 1. The relativity of time, 2. Black holes in spacetime, 3. The Harvard Cower experiment, 4. The world's most accurate clocks, and 5. Why time dilation actually matters. Let's get into it. Section 1. The relativity of time. Let's take a look at Einstein's bold prediction. Way back in 1907, Albert Einstein had this profound realization. He figured out that an accelerated reference frame is physically equivalent to a gravitational field. And that staggering insight led to what we call gravitational time dilation. Now, it is absolutely crucial to get this. We're not talking about an optical illusion or a mechanical failure of a clock. It is an actual physical difference in how much time elapses between two events. The rule here is surprisingly simple but totally mind-blowing. The lower the gravitational potential, meaning the closer you are to a super heavy mass like a planet or a star, the slower your clock ticks compared to someone standing way out in deep space. You are literally aging slower than someone who is far away from that gravitational pull. Crazy, right? Moving on to Section 2, black holes and space-time. We're looking at extreme gravity and the Schwarzschild geometry. Let's look out into the cosmos and see how this builds when we're dealing with the most massive objects in the universe using what physicists call the Schwarzschild metric. If you want to understand just how extreme this gets, modern physicists actually use computational simulators written in Python to model the relativistic effects near supermassive black holes. And to do this, they basically adjust 3 core dials to see what happens to spacetime. First, there's the mass of the black hole, which dictates the raw strength of the gravity. Second, the distance offset, meaning, exactly how close you dare to get to the anomaly. And third, the spin parameter, which accounts for the black hole's rotation. Tweak any one of these dials and you fundamentally alter how time and space behave in that area. If you were to plug those parameters in and take a hypothetical journey out there, you would be facing some brutal gravitational realities. As you get close, you hit the event horizon. That's the absolute point of no return, where not even light can escape. Further out, you've got the photon sphere, a region where gravity is so intense that light itself actually gets trapped in orbit. Cross the wrong threshold and you'll experience spaghettification. And yes, that's a real scientific term where tidal forces literally stretch your body into thin strands because the gravity at your feet is just vastly stronger than the gravity at your head. To even survive this journey, you've got to stay at the innermost stable circular orbit, or ISCO. And if the black hole is spinning, you get frame dragging, where the sheer mass of the thing drags the actual fabric of spacetime around with it, like water swirling down a drain. To really wrap your head around this staggering physics, just think of space itself as a river. Inside the event horizon, that river of space is flowing inward faster than the speed of light. Now, imagine photons of light as canoes paddling furiously upstream. Outside the horizon, sure, they can make some headway against the current, but inside, no way. The current is so incredibly fast that it overpowers even the ultimate speed limit of the universe, carrying everything, matter, light, and time itself, inevitably downstream to be crushed at the central singularity. Section 3. The Harvard Tower experiment. Let's see how they prove this theory right here on Earth in 1959. Now, it's really easy to just dismiss all this black hole talk as cosmic science fiction that has absolutely nothing to do with our daily lives. But physicists Robert Pound and Glenn Repka wanted to prove Einstein's equivalence principle right here on our planet. To measure a time distortion so unimaginably small across a mere 22.5-meter tower at Harvard's Jefferson Laboratory, they had to invent a truly ingenious setup. First, they placed radioactive iron-57 at both the top and the bottom of the brick tower. Then, they used a vibrating speaker coil to continuously alter the Doppler shift of the emitted gamma rays. This hyper-precise vibration allowed them in step 3 to measure the absorbed gamma rays at the other end using a newly discovered quantum phenomenon known as the Mossbauer effect. And the results? Absolutely astounding. They successfully measured a fractional frequency shift of minus 2.56 times 10 to the negative 15th. That is an almost unfathomably tiny shift in the frequency of the gamma rays as they traveled up and down in Earth's relatively weak gravity. But it was there, and it directly proved Einstein's theory to a 10% margin of error. Just think about the sheer magnitude of that achievement for a second. These scientists literally weighed light inside a brick building in Massachusetts, proving once and for all that time runs slightly slower at the bottom of the tower than it does at the top. All right, section 4, the world's most accurate clocks. We are taking atomic clocks to new heights.
The quest to measure time dilation definitely didn't stop with Pound and Repka in '59. It has steadily escalated right alongside modern metrology and quantum technology. Just look at this incredible progression of scientific proof. We start with pure mathematical theory on paper from Einstein in 1915. Decades passed, and we get the stationary Pound-Repka tower experiment in '59. Jump to 1971, and Hafele and Keating take it a massive step further, literally putting actual atomic clocks on commercial airplanes and flying them around the world to show that the flying clocks lost sync with the ones left on the ground. And now, looking toward 2025, scientists from the National Institute of Standards and Technology are taking next-generation optical lattice clocks to the peaks of Colorado mountains to push this to the absolute extremes. In that cutting-edge 2025 experiment, researchers took a highly complex, ultra-precise ytterbium optical clock all the way up to the summit of Mount Blue Sky, which sits at a whopping elevation of 14,130 feet. Then, they connected it via a massive optical fiber to another identical clock sitting 9,000 feet lower in a laboratory in Boulder. They are literally pulling these incredibly finicky quantum instruments out of a perfectly controlled lab environment and throwing them out into the wild to test time dilation over a massive vertical drop. And sure enough, the clock on the mountain, which is experiencing slightly less gravity, actually ticks faster than the clock down in the valley. But hey, we aren't just scaling mountains here, we're tracking this distortion of time in the actual vacuum of space. The European Space Agency's ACES mission compares Earth-bound atomic clocks to clocks mounted on the International Space Station. Get this, these instruments are so hyper-accurate that they would drift no more than 1 single second over the span of 300 million years. Because the ISS is moving incredibly fast, but also sitting in lower gravity than the Earth's surface, scientists can measure the exact competing relativistic effects on time itself to an unprecedented level of accuracy. Section 5. Why time dilation matters. Moving from theory to everyday engineering. So, at this point, you might be wondering, why does any of this matter to my daily life? Well, the answer is literally sitting in your pocket right now. Global Positioning System satellites, or GPS, must be corrected by exactly 38 microseconds every single day. Here's how the math shakes out. Because the satellites are moving so fast in orbit, special relativity actually slows their onboard clocks down by about 7 microseconds a day relative to us. But because they're further away from Earth's mass and in lower gravity, general relativity speeds them up by 45 microseconds. That leaves a net difference of exactly 38 microseconds. If we didn't program that exact relativistic correction into the software, our entire global navigation network would lose its pinpoint accuracy and fail completely within a matter of minutes. Think about that. What began as an outrageous theoretical framework by Einstein, just a purely mathematical concept of how space and time interact, has evolved into a practical, unshakable engineering necessity today. We literally require these exact relativistic calculations to do the things that power our modern world. We use them to predict earthquakes by measuring tectonic shifts, to accurately map the Earth's surface, to synchronize global financial networks, and to successfully route your car to the grocery store. It really leaves us with a profound realization, challenging us to look at our universe completely differently. I mean, if the sheer heavy mass of a planet literally bends the flow of time itself, making clocks tick faster or slower depending purely on where you happen to be standing, what else about our reality is just a matter of perspective? It challenges us to ask what other fundamental truths of our existence are just sitting out there, waiting to be uncovered by the next generation of curious minds. Thank you so much for joining me on this explainer. I really hope you found it as fascinating as I do.